好，各位应该好，我们现在的场是由 IDS 的 DETEKT 来为我们讲解 DETEKT 这个技术，它是一个 Aerosol base 的点胶技术，它是用气流带动我们的墨水到我们的基板上面，那它最小猎鹰尺寸是大概落在20到25麦克之间。那待会他会用英文来为我们讲解这个技术。那如果中间有问题，可以就是提问，或是可以用中文或者用英文，然后我们再帮你转给他也可以。那如果没有问题的话，我们可以，如果之后一时间还没有其他问题，我们可以的，应该说如果之后有问题，可以再 pass 给我们，我们再帮你转达，再转询问也可以。好，那就让我们来请DETEKT 来为我们讲解那种DETEKT 的技术。Okay, David. Yeah, I finished. You can start your presentation now.
Okay, start now.
Yeah.
Okay. Yeah. Hi, this is Dave Kaiser from IDS in Albuquerque, New Mexico. And today we want to introduce the NanoJet aerosol printing technology, what we consider to be the next generation in aerosol printing. So IDS, so Marcelino and myself, we are working to develop this next generation technology and have over 30 years combined experience. And we were developed and commercialized the first generation technology and are excited to introduce this next generation aerosol printing technology. The things that, so the NanoJet technology provides a robust print performance with and we've demonstrated more than 8 hours consistent runtime without operator intervention and very stable operation. Because of the way that the aerosol is collimated, we actually get very good line quality, and we also get reliable and consistent line widths over the 8-hour period. We can print lines down to as small as 10 microns and up to a couple, maybe as much as 200 microns wide. We also have a single material or a dual material print option where you can print more than one material from the same nozzle. Through the simplification of the aerosol print design, we've made the system easy to operate and maintain, and actually provide a significant or a fractional cost compared to the first aerosol printing technology. So the aerosol printing technology can be used in a lot of different application areas. We can print conductive materials, dielectric materials, and a variety of other materials. Conductive and dielectric materials really provide the opportunity to print multi-layered, multi-material circuits. We also are looking at printing semiconductor interconnects, and in one application we're trying to replace wire bonding, where you transition the circuit from a soft substrate to a hard substrate, where wire bonding can damage the soft substrate. We're also able to do print the conductors and electrical circuits for molded interconnected devices. And then the technology has a unique capability to be able to print up over vertical surfaces. And so we're looking at 3D printed interconnects as well. What we've done is really try to understand the technology better. And most aerosol sources are polydispersed, meaning that they have a broad range of droplet sizes. And so we were able to leverage a technology from Sandia National Laboratories and that uses hydrodynamic and aerodynamic focusing and multiple lenses to be able to collimate the aerosol stream very, very well. And that provides really good printed line quality. We also were able in our design to minimize the travel of the aerosol stream to make sure that there's very few points for material collection that typically would lead to overspray or satellite droplets. And that's sort of the basis for the NanoJet technology. One of the innovations, the NanoJet print technology, the print head consists of 3 major components. Where you have a removable ink cartridge that contains the aerosol, the ink, and it's where the aerosol is created. The atomizer base has the transducer, the ultrasonic transducer that provides the energy to create the aerosol within the ink cartridge. And then the flow cell actually has the focusing elements to focus the aerosol to a fine stream for printing. The atomizer base also provides the attachment point to the motion platform. The image on the right shows the type of line quality that we're able to achieve now. And we can, this is a 35 micron wide line. We can achieve the same kind of printed line quality for much narrower lines as well. So the aerosol is generated inside the print cartridge. The print cartridge inserts into the atomizer base. And since there are no external feed lines for the aerosol, and there's some unique features within the ink cartridge, there's really little chance for clogging to occur within the print head. And so using that, what we've done is be able to avoid satellites and overspray. And this really, the design and minimum travel length for the aerosol really gives us a long runtime, reliable performance over long periods of time. And we actually have done a lot of work to understand this and collect data to kind of validate and support our claims. So we actually have run a lot of stability tests. A lot of the early stability tests we ran on the print head were 4-hour tests. And more recently, we've run several 8-hour print tests. And in this particular case, we actually used the 4-hour test and just ran it twice. Once we finished printing, we actually ran it again. The parameters, print parameters, are shown on the left here in the table that we use for printing. And then our test procedure was that we would establish the optimum printing conditions. Then we kind of, clean the head and make sure there's plenty of ink, and then and we would start that printing, or the print head printing. We would move to a park position where we would dump the material into a location. We continuously flowed the ink through the head for the entire 8-hour test period. Periodically, we would print lines for analysis after the print tests were completed. Once the print tests were completed, we would actually cure the samples, and then we would do optical analysis of the printed lines to measure the width, as well as to measure resistivity of the printed lines. These images show some of the printed line quality that we're able to accomplish on our 8-hour test. The lines on the left show the printed lines and measured line widths for the lines from 20 to 60 minutes. Each set of lines is printed every 10 minutes. On the right, it shows the printed lines that were printed towards the end of the test, at the end of the test. And you can see there's a slight, you can maybe say there's a slight change in the printed line width, but it's pretty consistent for the full 8-hour period. So we actually plotted that. We measured the line widths on this data, and then we actually plotted the data on this shown here in the graph. It was kind of nice that we actually did the 2 4-hour tests. It shows that there's an initial, when you first start, the areas circled in red show that there's an initial phase where there's a little bit of instability in the print head where it has to warm up. But then once it warms up, you actually get very consistent printed line widths over the entire 8-hour period. So we measured the line widths to be an average of about 68 microns. The statistical analysis showed the standard deviation to be about 3.7 microns, and then the tolerance on the printed lines was about 5.5%. So we felt like this is a pretty good test and pretty good performance for the print head. And we repeated this test multiple times. The image on the right shows the kind of line edge quality that we can get with the aerosol printing, the nanojet printing technology. Because we're using multiple lenses and stuff, we can really get good focusing of the aerosols, and very little overspray or anything on the edges. And so we really use 2 different focusing techniques. We use a hydrodynamic approach coupled with aerodynamic focusing. And then what we licensed from Sandia Labs was The fact that we can use multiple aerodynamic lenses in the system to collimate the entire aerosol distribution. So the first lens will collimate the largest droplets, the next lens will collimate the droplets in the middle, and then the third lens will collimate the droplets in the smaller sizes. And this really gives us superior line edge quality. You can see the lines are smooth and straight. And then we are able to control the line width or get consistent line widths over long periods of time, which is really, really good for production and stuff like that. One of the unique attributes of the aerosol printing is that the distance from the nozzle to the substrate can be between 1 and 5 millimeters. And this, allows you to print over surfaces with a lot of topography. And then we also have an internal shutter that we've patented, and that allows us to kind of maintain area around the end of the nozzle to be clean and free so that you can access tight spots and stuff. We're continuing to evolve the technology and improve the print performance. The lines shown here on these images show recent results using a humidification technique to kind of really help prevent the droplets from drying out. And so we get to really crisp line edges and no overspray or satellites to speak of. We actually work with a variety of different customers. So we work with this pattern shown here is for an aerospace customer, and they really wanted us to sort of show that we could print their pattern and that we could actually the system would perform as we advertised. And so the printed line features on these were as small as 100 microns, which isn't too small for our printing technology. The more significant thing is that we printed consistently for 70 minutes, and they were really happy with the quality of the print. And so that's really good. And these types of runs are very consistent, or we do these types of runs a lot with our systems. This is a circuit that's printed for an implantable device stimulator. Shows some of the finer line features as well as how the internal shutter works. And the features on the right, the printed narrow lines are about 30 microns wide. This image or video shows printing over a polyurethane membrane or bladder. And you can see that the working distance for the nozzle between the nozzle and substrate is, several millimeters. And and the beam is collimated, so it's relatively insensitive to the focus position. But it shows the capability or the ability to print over non-traditional type structures and surfaces. So the removable ink cartridges are unique to the NanoJet technology. And the cartridge is a self-contained ink reservoir, and all the aerosol generation occurs within the ink cartridge. The ink cartridge is inserted into the atomizer base. The ink cartridges are nice because it really facilitates a quick changeover. So if you are doing production, you run out of ink, you can pause the process, replace the cartridge with a full cartridge, and then go maintain it offline. It's actually real easy and safe for the operators to service the cartridges, and then the dual material configuration allows both conductive and dielectrics to be printed from a single head. So this slide shows in the middle you see the print head with the ink cartridge and the flow cell separated from the atomizer base. And so this is how it can be disassembled into components for servicing or cleaning. Since there's a couple of clamps on the side of the cartridge that allow the cartridge to be removed, and there's an air inlet line that has to be removed. In a similar fashion, the flow cell on the bottom where the focusing occurs can be unscrewed from the print head and serviced and cleaned separately. The images on the right for the ink cartridge and the flow cell show how the ink cartridge and flow cell can be broken down into a few components that can then be, ultrasonically cleaned in a solvent or a fluid, and then blown dry and put back into service. So what really helps with the print head, it makes it pretty reliable, is that there is no external plumbing in the print head to transport the aerosols. Then there's some features within the ink cartridge itself that allow the aerosol to be reused and recollected into their ink reservoir. And so there's very little places for the aerosol to be trapped, where it would form a puddle and then ultimately lead to clogging. And that's one of the unique attributes of the system. The video on the right shows printing of a spiral conductor onto a 750 micron diameter pin. And this was used for an accelerometer sensor. And down on the video on the bottom is showing printing of about 60 micron wide lines for a redistribution circuit. And again, you can see that for both of these, there's a lot of working space between the nozzle and the printed substrate. So because we've been able to simplify the design considerably, the NanoJet technology is quite economical. We've been able to lower the acquisition costs for the customers, and that's a real benefit. And the operating costs, the system is really simple, so you don't have to spend a lot of time maintaining it or servicing and cleaning and stuff. So that really helps with the operating costs. The mean time between a system, mean time between failure, we believe it meets the industry expectation. System's easy to integrate and operate, and adapts to most motion platforms. So in conclusion, we really feel like we've made up a real breakthrough in this next generation aerosol printing technology, the NanoJet technology. We've demonstrated that we can get better print performance. We can have a very reliable print process and prints for long periods of time consistently. We've maintained the dimensions of the printed lines. We have a better operating model, and we also have a better cost. So we'd like to say that the IDS NanoJet technology is better than the previous technology we worked on. So I'd like to thank you for your time. And if you have any questions, we could take those.
No, thank you for your presentation.
Do you want me to stop sharing?
So thank you for your presentation. Yeah.
You're welcome.
Anyone have question? Yeah, David, I have question about your NanoJet. Yeah. Did you hear? Yeah. Hello. Hello.
I can't hear.
Yeah. Yeah. I see the your presentation and your PPT show the replace the ink cartridge is very easy. And did you calculate the replace time? I mean the time, yeah, to replace it for one time replace your cartridge.
So the time to replace the cartridges and stuff?
Yeah. Yes.
It's less than a minute. There's two clamps on the side and one gas line to replace the ink cartridge. So it's a minute or two.
Okay. So if I want to print different ink, can we prepare more ink cartridge to do press? I mean, can we prepare more ink cartridge to increase the press process?
So to switch from one ink to another ink?
Mm-hmm. Yeah.
Yes. So what you would do is disassemble it like we've shown in the one picture, and then clean it if you were going to a different ink. An option would be to have multiple ink cartridges too, because then you can actually, if you have the ink in the ink cartridge, you can actually store the ink in the ink cartridge.
Okay.
Yeah.
Okay. Thank you.
Yeah, David.
Yes.
Yeah, I'm Peter Chu. Sorry for just log in so late because I have another meeting.
Oh, that's okay.
So,
Thanks.
may I ask you two questions from our Semicon Fabs users?
Yes.
The first question is related to by your experience and for almost 20 years to develop Aerosol-based solution. Is it possible to make no overspread by nanojet solution without overspread? Do you think do you think it is possible?
So I think it is I think it is possible. I think that the solution that we have now with certain inks works really well. We are working to kind of increase the droplet size and get rid of so the overspray is largely a result of the very, very small aerosol. And so if we can remove the smallest droplets, then we can completely get rid of overspray. And,
Okay.
and
so
we can also add extra lenses to help in the print head.
So how many lenses you have right now for your commercialized dispenser?
So there are 2 lenses right now. We're going to be adding a 3rd lens. We're doing a lot of
2 lenses. How is the finest printing lines by 2 lenses inside the on your NanoJet dispenser?
Okay, so we've printed down to about 10 microns
10 micron.
wide. Yeah, the University Rochester Institute of Technology have recently has some lines that they printed that are 5 microns. They were not real fast, so very much research.
So in this case, whenever we print in the very fine line width, say 10 micron,
Yes.
how large is the overspray will come out?
It's hard to say for sure. I mean, it's pretty. It depends on the ink and the process conditions. It can be pretty clean. The lines can be very clean.
Okay, got it. Okay, thank you. The second question, we are going to have the 3D interconnector solution. So, do you have any solution to make 3D interconnectors printing requirement? What I mean, the very high throughput.
So we are working on that now. We are able to, so that was a project we're working on. I was hoping to have some preliminary results for this talk, but we ran out of time.
Okay, it's good. Okay, thank you.
You're welcome.
Yeah, Daniel. Okay. Okay, thank you. Yeah, David. So I know it's very late in Albuquerque, New Mexico. So So do you take a look at our booth via Daniel's camera?
Yes.
Oh yeah.
It looks nice.
Oh yeah.
You guys are actually able to go to a show too, which is really nice.
Oh yeah. So that means you also stay at the show. You don't need you just stay at home. Okay. Thank you. Okay, appreciate your time and your very great presentation today.
All right. Thank you, Peter.
Okay, thank you, David.
Thank you. Thanks, Daniel. You guys have a good day.
Bye-bye.
Bye. See you, Daniel. Take care.
See you. Yeah.
Enjoy the rest of the show.
Okay, thank you. Yeah, good.
Bye now.
Good night. Yeah.
Right.